Welcome to Midnight Physicist. The night is deep, stretching endlessly, and within it lies a story untold. You are floating in space, where nothing feels solid beneath your feet, but every part of you feels the pull of something immense. The stars twinkle softly in the distance, each one a beacon in the inky blackness that stretches forever. Imagine the stars as ancient storytellers, their lights traveling across the universe for millions of years before finally reaching your eyes in the quiet of the night. Their soft glow seems to speak as if they carry the wisdom of eons within them out here. In the vastness, time and space intertwine in ways that are difficult to comprehend. The light from the stars you see tonight may have traveled from galaxies that are no longer there, their light a message sent long before you were born. The sky is like a book, each star a chapter filled with stories, some so distant that they're still only half. You wonder, how far does this book stretch? How many pages are yet to be turned? As you float further, the darkness of space begins to feel less empty and more alive. It hums with the presence of things unseen, of energies and forces that are hidden from your sight, but not from your imagination. The planets, distant and mysterious, orbit in a delicate dance, held in place by an invisible thread of gravity. This invisible force, ever present, is the quiet architect of the cosmos, guiding the stars and planets in their eternal movements, making sure they never stray too far from their paths. Now, imagine that you are not alone. The universe is full of whispers, whispers of other explorers, distant travelers who, like you, have wondered what lies beyond the horizon. Perhaps they too have gazed up at the stars and felt the same longing, the same question: what is out there? The beauty of space, vast and immeasurable, can be overwhelming. It's easy to feel insignificant, a tiny speck in the grand expanse of the cosmos. But take a deep breath. It's not about how small you are in the universe. It's about the question that burns within you, the question that has driven humanity for centuries. What lies beyond? You begin to wonder about the time it takes for light to travel. Light travels at an incredible speed, yet even at this speed, it takes years, sometimes millions of years, to reach us. When we look at the stars, we are seeing them as they were in the past, not as they are now. The farther you look into space, the further back in time you peer, as though you are looking into the very beginning of everything. The universe is a time machine, and you are traveling along with it, watching the past unfold in the light of the stars. And yet, space is not just a place of vastness. It is a place of infinite possibility. Within the darkness, there is a silent promise of discovery. Scientists, philosophers, and dreamers have all pondered the mysteries of space, and they too have looked up with wonder in their eyes. For them, each discovery, each new star, each new planet, each new moon is a small step towards understanding the grand design of the universe. Their curiosity is unquenchable, their quest for knowledge boundless, and they press on, knowing that there is always more to uncover. Your mind drifts to the question of life. In this vast, uncharted expanse, could there be others like you, wondering the same thoughts? The possibility is as vast as the universe itself. Somewhere, far away, another being may be staring up at their night sky, pondering the same questions that you are. The idea that we are not alone in the cosmos, that there are other stars with planets that could harbor life, fills you with a sense of awe. It is a quiet, hopeful thought, a thought that stirs a longing to explore further, to seek out the unknown. But as much as the universe beckons, it also remains elusive. There are questions it will not answer, mysteries that will remain hidden. No matter how far we venture, the vastness of space is a mirror reflecting our own desire to know, to understand, to connect. Yet, space is a reflection of something deeper within ourselves, our yearning for meaning, our search for our place in the cosmos. You float a little further, past stars that flicker like the embers of a long extinguished fire, past galaxies that swirl in magnificent patterns. The silence of space is profound, but it's not empty. It hums with the life of a universe in motion. Every star, every planet, every particle is a part of the same grand rhythm, the same cosmic symphony that has been playing for billions of years. You are a note in this song, a fleeting moment in the infinite stretch of time, but you are here. And that in itself is a small miracle. As your mind continues to wander, you begin to understand that the mystery of space is not just in the stars or the planets, but in the act of asking the question. The search for knowledge, the desire to understand, is part of what makes us human. It is what connects us not only to the stars, but to each other. The more we learn, the more we realize there is still to discover. And this journey of understanding is something that will never end. And so, as you float here in the quiet of space, with the universe unfolding around you, you are reminded of one simple truth, that the journey is just as important as the destination. The quest for knowledge, the drive to explore, the desire to understand. These are the things that keep us moving forward through the vast unknown. The universe may be a mystery, but it is a mystery that is ours to unravel, piece by piece, thought by thought, star by star. As you let this realization settle into your mind, the stars begin to fade, their glow dimming as if to tell you that your journey is far from over. There is more to see, more to understand, more to learn. And though the answers may never come all at once, they will come in their own time. For now, you are content to simply drift, knowing that you are a part of something far larger than yourself, and that the questions you ask are the very things that will carry you forward. Space is not empty. It is not a mere void, a dark hole between the stars. Instead, it is the stage upon which the universe dances, a grand stage of infinite possibilities. Imagine, for a moment, that you are floating in the vastness. You are not weightless in the sense that you have no form, but in the sense that here, in the immense quiet of space, the rules that govern you on Earth no longer apply. There is no ground beneath you, no air to breathe, and yet you exist, not in isolation, but in connection with the very fabric of the universe. Space surrounds you, stretches endlessly in all directions, a vast ocean without shores, without borders. But it is not a silent space. It hums with potential, with energy, with the flicker of stars that were born millions of years before your thoughts even began. It whispers in wavelengths beyond the range of human hearing, in the pulsations of distant galaxies, in the cosmic radiation that fills the emptiness. Space is not void. It is full, but not in the way we usually think. The first thing to understand about space is its scale. It is vast beyond measure, stretching out in all directions. To the untrained eye, it may seem like a dark, empty sky filled with distant pinpricks of light. But these lights are not just stars. They are suns, burning with the same fire that gave birth to our own sun, and they are far, far away. The closest star to Earth, Proxima Centauri, is over 4 light-years away. That means the light you see today from that star left it more than 4 years ago. When you look up at the night sky, you are looking into the past, seeing a history written in the light of distant stars. And yet, even the vast distances of space are not quite as they seem. Space itself is not static. It is constantly stretching, expanding, as if the very fabric of the universe is being pulled apart. Imagine a balloon being inflated. As it expands, everything on the surface moves away from everything else. In space, it is the galaxies that are being carried apart by the stretching of the space between them. This is the expansion of the universe, a phenomenon that has been happening since the Big Bang, the moment when time and space themselves began. This expansion is one of the great mysteries of space. How could something as infinite as space expand? If it is already boundless, what does it mean to stretch it further? The answer, it seems, lies in the nature of space itself. Space is not a thing to be filled or emptied. It is not a container for the stars, planets, and galaxies. Instead, space is the medium in which all things exist, and this medium is ever-changing, ever-flowing. It is not just the backdrop to the universe, but an active participant in it. Every galaxy, every star, every planet is embedded in space, moving within it, shaping it as much as it is shaped by it. There is a quiet beauty in this idea. Space is not something that simply exists around us. It is woven into the very fabric of reality. It is the stage and the actors, the composer and the symphony. Space and time, it seems, are intimately connected. They are not separate entities, but 2 parts of the same whole. When we talk about the fabric of space-time, we are speaking of the way that time and space are interwoven, how one bends and shapes the other. Imagine placing a heavy ball on a stretched-out piece of fabric. The fabric dips and curves under the weight of the ball. Space behaves in a similar way. The presence of mass, of stars and planets, causes the fabric of space to curve and bend, creating the force we call gravity. And in this way, space is not just an empty stage. It is a living, breathing entity, full of energy and influence, shaping the very course of the stars. Yet, for all its mystery, space is not just a place for celestial bodies. It is also the birthplace of ideas, of dreams, of human curiosity. It is space, after all, that inspires us to look up, to wonder, to ask the big questions. What lies out there? What is the meaning of it all? These questions echo in our minds, and it is space that invites us to explore them. It is this boundless realm, with its infinite expanse, that ignites the spark of discovery in our hearts. In every direction, there are mysteries waiting to be uncovered. Consider the stars, those burning orbs of light. Each one is a furnace, a place where nuclear reactions take place, where elements are born and destroyed in the heart of a star. The very atoms that make up your body were once forged in the hearts of stars long gone. And as you gaze up at their light, you are gazing into a past that is both distant and familiar, a history that is both yours and the universe's. But space is not just a place of stars. It is also the home of planets, moons, and asteroids, each one a unique world in its own right. The Earth, where you live is one of many, yet it is the only one we know to harbor life. The fact that life exists here in the midst of this vast, empty universe is both a wonder and a mystery. It raises the question of whether life could exist elsewhere, on other planets, orbiting other stars, in other parts of the cosmos. Could there be other places where life has taken root, where beings like you gaze up at their sky, wondering what lies beyond? The beauty of space is that it is full of both certainty and uncertainty. We know so much about it, and yet there is still so much we don't understand. Space is full of questions, but it is also full of answers, answers waiting to be discovered, waiting for the right questions to be asked. The more we learn about space, the more we realize how much there is yet to explore. Each discovery opens up new possibilities, new mysteries to ponder, new truths to uncover. As you float through the expanse of space in your mind, you come to a quiet realization. Space, in all its vastness, is not just something to be understood, it is something to be felt. The beauty of the cosmos is not just in the knowledge we gain, but in the way it stirs something deep inside us, a sense of wonder, a sense of connection to something greater than ourselves. In this moment, as you drift through the stars, you realize that space is not just out there. It is inside you, too, stretching within you, expanding as you expand your understanding of the universe. You are part of this grand tapestry, a thread woven into the infinite fabric of existence. And as the stars twinkled gently in the distance, you feel the quiet hum of the universe around you, calling you forward, forward. Imagine the beginning of everything, when there was no time, no space, only a single point, dense and infinitely small. There were no stars, no planets, no galaxies. There was only potential, waiting for a spark to set it all in motion. This is where our story begins, in a moment of such extraordinary energy that it defies imagination. This is the birth of the universe, a moment we call the Big Bang. The Big Bang is not an explosion in space. It is the creation of space itself. Before the Big Bang, there was no outside to explode into. The universe, as we know it, was contained in a singularity, a point so dense that everything, all the matter, energy, and space, existed in it. And then, in an instant, that singularity began to expand. The Big Bang was not an explosion in the way we typically imagine, a burst of fire and sound. It was an expansion, a stretching of space itself. From that one point, space began to unfold, and the universe started its journey. As you float through this moment, imagine the universe as a balloon. At first, it is tiny, smaller than the smallest dot you can imagine. But then, as the balloon inflates, it stretches, growing larger and larger with each passing moment. This is the expansion of the universe. In the beginning, all the matter and energy that would become the stars, the galaxies, and everything we see today was contained in an incredibly small space. As the universe expanded, it cooled, and the first elements began to form. These elements, like hydrogen and helium, are the building blocks of stars and galaxies. They spread out into the universe, gathering together to create the first light. The universe, at this stage, was not filled with stars, but with a glowing fog of particles, radiation, and energy. Over time, as the universe cooled, this fog began to clear, and stars began to form. The first stars were not like the stars we see today. They were larger, hotter, and shorter lived. But they were the seeds of galaxies, the first sparks of light in an otherwise dark universe. And as they burned, they forged heavier elements, elements that would later form the planets, the life, and everything else. You might wonder, how can something as vast as the universe begin from such a small point? The idea seems almost impossible, but this is the reality we live in. Space and time themselves were created in that moment of the Big Bang. In a sense, time began with the Big Bang, and the universe began its journey through time and space, expanding outward with each passing moment. The space between objects, the distances we measure, grew as the universe grew. As galaxies and stars drift apart, they are not moving through space as we might think, but are carried along by the stretching of space itself. The universe is like a fabric that is constantly expanding, and as it stretches, everything within it stretches too. One of the most fascinating aspects of the Big Bang is that it did not stop after the initial explosion. It is still happening. Today, the universe is still expanding, still stretching outward. When scientists first realized this, it was a moment of profound discovery. If the universe is expanding now, it must have been much smaller in the past. By measuring how galaxies move away from us, scientists can look backward in time and trace the expansion all the way back to that moment when the universe began. They call this the redshift, a stretching of light waves as the universe expands, a kind of cosmic echo of the Big Bang. This discovery led to a realization: the universe has a history, a story that stretches back to its origin. When we look at the night sky, we are not just seeing stars. We are looking into the past, into a time when the universe was young. The light from distant galaxies has traveled across time and space to reach us, and in this light, we can trace the journey of the universe from its birth to the present. In a way, we are all connected to the Big Bang, not just by the space we occupy, but by the very atoms in our bodies, atoms that were formed in the early moments of the universe, when the first stars exploded in supernova, scattering their elements throughout the cosmos. In the beginning, after the Big Bang, the universe was a very different place. It was filled with an ocean of energy, an ocean of particles and radiation that swirled around, too hot and dense for anything to form. But as it cooled, the first atoms began to form. First, hydrogen and helium, the simplest elements. Then, over billions of years, more complex elements were created in the hearts of stars. Stars are like factories, forging the elements that make up everything around us. The carbon in your body, the oxygen in the air, the iron in your blood, all of these elements were created in the hearts of stars that lived and died long before Earth even existed. The Big Bang Theory also suggests that the universe has no center, no fixed point from which it began. Instead, the universe is expanding everywhere, in every direction. This means that every point in the universe is moving away from every other point, and from our perspective, every galaxy seems to be moving away from us. It's not that we are at the center of the universe, it's that the universe is expanding from every point, and this expansion is what gives the illusion of galaxies moving away from each other. One of the most profound implications of the Big Bang Theory is the idea that the universe is finite in age, but infinite in size. While it has a beginning, the moment of the Big Bang, the universe will continue to expand forever. We may never reach the edge of the universe because there is no edge. The universe will continue to grow, to stretch, to evolve. In this way, the Big Bang was not just the beginning of space, but the beginning of everything: time, matter, energy, and the very possibility of life. As you think about the Big Bang, you realize how little we still know. The questions remain. Even as we uncover more and more about the universe's birth, what happened in the first moments after the Big Bang? What caused the initial expansion? And how did all the complexity of the universe arise from such a simple beginning? These questions remain at the heart of science. As we seek to understand the origin of everything, the mystery of the cosmos, the wonder of creation, space is vast, much too vast to measure with a simple ruler or a compass. The distances between stars, planets, and galaxies stretch far beyond our imagination, creating a sense of awe that leaves us wondering, how do we even begin to measure something so immense? To answer that question, we must first understand that space itself is not an empty container, but a dynamic and ever-changing expanse. It is the very medium in which all of existence occurs. And while measuring this grand canvas might seem impossible, humanity has developed a way to bring it within reach. We measure space not in traditional units like inches or miles, but by utilizing the speed of light, the passage of time, and the relationship between objects within the cosmos. The first step in understanding how we measure space is to think about light, the fastest thing we know of. Light travels at a mind-boggling speed of 299,792 kilometers per second, a speed so fast that it can circle the Earth more than 7 times in just 1 second. Light is the key to measuring the vast distances of space because it allows us to see things far beyond the reach of our eyes. But even more fascinating is that light also brings with it a clue about how far things are. Time. When we look at a star in the night sky, we are not seeing it as it is at this very moment, but as it was when the light left it, sometimes millions or even billions of years ago. The further a star is, the longer its light takes to reach us. This journey of light, traveling through space, gives us a unique way to measure distance. We can measure how far light travels in a given amount of time, and by that, we can calculate how far away an object is. This unit of measurement is called a light year. A light year is the distance that light travels in 1 year, about 9.46 trillion kilometers. When we say a star is 10 light years away, we are saying that the light from that star has been traveling for 10 years to reach us. In other words, when we gaze at stars that are 100 light years away, we are looking back in time, seeing them as they were 100 years ago. Each star is a time capsule, and light is our messenger, bringing information about the past from the farthest reaches of space. But light years, while useful, are just the beginning. As we look further and further into the cosmos, the distances become so vast that even light years feel too small. Enter the parsec, another unit of measurement used to describe the larger distances between stars. 1 parsec is roughly 3.26 light years, and it is the unit astronomers use when measuring the distances between stars in our galaxy. The parsec gets its name from the concept of parallax. a method used to measure the distances to nearby stars. Imagine you are standing in one place and looking at an object. If you change your position, the object seems to shift against the background. This is parallax. By measuring how much the position of a star appears to shift when observed from different points in Earth's orbit, astronomers can calculate how far away it is. This shift is incredibly small, but it gives us the precision to map the positions of stars with astonishing accuracy. The parallax method works well for nearby stars. But what about objects that are far, far beyond our own galaxy? To measure these vast distances, we must look to other methods. One such method is the redshift, which is based on the Doppler effect, the same phenomenon that makes a car's engine sound different as it approaches and then passes you. In the case of light, when an object in space is moving away from us, its light stretches out, shifting toward the red end of the spectrum. The greater the redshift, the faster the object is moving away from us. By measuring this redshift, astronomers can determine the speed at which distant galaxies are receding from us, and from there, calculate their distance. This discovery was a groundbreaking moment in understanding the universe. In the early 20th century, astronomer Edwin Hubble observed that galaxies farther from us were moving faster than those nearby. This led to the realization that the universe itself is expanding, a discovery that not only changed our view of space but also confirmed that the universe had a beginning, the Big Bang, some 13.8 billion years ago. But measuring space is not just about distance. There is also the question of size. How do we measure the size of an object as immense as a planet or a galaxy? For planets, we can use something called angular diameter. Imagine holding a coin in front of your face and looking at it from different distances. As you move the coin closer, it appears larger, and as you move it away, it appears smaller. Using this principle, astronomers measure the apparent size of planets and stars from Earth. By knowing the distance to the object, they can calculate its actual size, just as you could figure out how large a coin is by knowing how far away it is when it comes to galaxies. Their size is measured in terms of their extent across the sky. Galaxies can be millions of light years across, containing billions of stars, planets, and other cosmic objects. But because the universe is constantly expanding, galaxies are not static. They grow, change shape, and even merge with other galaxies. Over time, by observing these interactions, scientists gain insight into the size and evolution of galaxies and can create models that predict their future development. Now, you may wonder, how do we measure something as intangible as the very fabric of space itself? This question leads us to the concept of space-time, which is the combination of space and time into one four-dimensional continuum. When we talk about measuring space, we are often referring to the warping and bending of space-time itself. The presence of mass, such as a planet or star, causes space-time to bend, creating what we experience as gravity. This bending can be measured, and through this, we can understand not just the distances between objects, but how objects influence each other through the fabric of space. This measurement of space-time, however, is still a topic of much exploration. The technology we use to observe the cosmos, such as telescopes, satellites, and probes, allows us to peer into the vast reaches of space. But our understanding of space itself is still growing. As new discoveries are made, are developed, our ability to measure space will continue to improve. Who knows what the future holds? Perhaps one day, we will be able to measure distances in ways we can't yet imagine, perhaps even directly measuring the expansion of space itself. As you reflect on these methods of measuring the universe, you realize that space, though vast and unknowable, is not beyond our reach. Each method, each tool we use, brings us one step closer to understanding the cosmos. Space may be infinite, but the questions we ask and the ways we measure make it just a little more comprehensible. And with each measurement, we find ourselves not farther away, but more connected to the universe around us. Space stretches before you, infinite and silent, as you drift through the cosmos. You gaze out into the vast expanse, the stars twinkling softly like ancient beacons. But in the stillness of this moment, a question arises, as it has for so many who have wondered before you. Is the universe truly infinite? Can something so vast and mysterious go on forever, with no end in sight? Or is there a boundary, a limit, a horizon that marks the edge of all that we know? To ponder this question is to dive deep into the heart of our understanding of reality itself. The universe, in all its grandeur, may feel limitless, an endless ocean of stars, galaxies, and cosmic dust. But is this feeling of boundlessness a reflection of reality, or is it a boundary we have yet to comprehend? The concept of an infinite universe is a long-standing mystery, one that stretches back to the early days of human thought. Ancient philosophers looked up at the night sky, and while they were filled with wonder, they also wondered whether the universe had an edge or whether it simply went on forever. In modern times, this question has taken on new dimensions with the help of science. As we now possess a deeper understanding of the cosmos and the forces that govern it, one of the key ways we approach this question is through the concept of the universe's expansion. In the early 20th century, astronomer Edwin Hubble made a groundbreaking discovery. Distant galaxies are moving away from us, their light stretched into longer wavelengths, a phenomenon known as redshift. This observation suggested that the universe is expanding, that the space between galaxies is growing larger with time. If we trace this expansion backward in time, we come to a moment where everything in the universe was once packed into a single, infinitely dense point, a singularity. This is the Big Bang, the moment when the universe began. The idea of expansion brings with it an important concept. The universe, as we know it, is not static. It is a living, breathing thing, stretching outward, growing with each passing moment. And yet, this expansion leads to another question. Does it have an end? If the universe is expanding, is it expanding into something? Or is it truly without boundaries, an infinite expanse that goes on forever, expanding but never reaching an end? This brings us to the idea of curvature. If the universe is expanding, we must ask, how is it shaped? Does it have a curvature, like the surface of a sphere? Or is it flat, extending endlessly in all directions? These questions are at the heart of cosmology, the study of the universe's structure. Scientists have proposed different models to explain the shape of the universe, and these models are crucial in determining whether the universe is infinite or finite. The most widely accepted model, based on current observations, suggests that the universe is flat, with no edges or boundaries, stretching outward forever. This model is consistent with the idea that the universe has been expanding ever since the Big Bang, and that the expansion will continue indefinitely. If the universe is flat, it would have no edge, no outside, and would indeed be infinite. But the possibility of a finite universe has not been ruled out. Some theories suggest that the universe could be shaped like a higher dimensional sphere, where the space itself curves back on itself. In this model, if you traveled far enough in one direction, you would eventually return to your starting point, like walking in a straight line around the surface of a globe. The universe would still be finite, but it would not have a boundary in the traditional sense. Instead, it would be a closed loop with no true edge, but still limited in size. Another intriguing possibility arises from the concept of the multiverse, the idea that our universe may not be the only one. In this view, there could be countless other universes, each with its own laws of physics and its own structure. These universes might exist alongside ours, separated by dimensions we cannot perceive. In this scenario, our universe could be finite within itself, but part of an infinite sea of universes, stretching far beyond the limits of our understanding. The notion of an infinite universe also brings us to the question of time. If the universe is infinite, does that mean it has always existed without beginning or end? Or did it, like a river, have a starting point, a moment of birth, like the Big Bang? If the universe is truly infinite, then the idea of time as we know it becomes more fluid, more difficult to grasp. Does an infinite universe mean an infinite past? Or could it be that the universe had a finite beginning, but will continue to expand into infinity for eternity? The cosmic microwave background, CMB, provides some clues to this question. This faint glow, left over from the early days of the universe, is a relic of the Big Bang itself. By studying the CMB, scientists have learned a great deal about the age of the universe, which is estimated to be about 13.8 billion years old. This evidence suggests that while the universe may seem infinite, its history is finite, bound by the limits of the Big Bang. And yet, the universe continues to expand, perhaps infinitely into the future. Despite all these theories and models, the question of whether the universe is truly infinite remains open, waiting for further answers. Our current understanding of the cosmos is constantly evolving, shaped by new discoveries and insights. And so, we are left with the possibility that the universe, vast and mysterious as it is, may hold its secrets for a long time to come. Perhaps the most profound realization is this: no matter how far we reach, how much we learn, the universe always holds more. Its vastness is not just a physical reality, but a reminder of the limitless potential for discovery and understanding. The universe, whether infinite or finite, is a mirror of our own curiosity, a reflection of the never-ending search for answers. As you drift through the cosmic sea, you begin to understand that the question of infinity is not just about space, but about the endless journey of thought. We may never fully know whether the universe is infinite, but in asking the question, we discover something far more valuable: the quest itself, the wonder, the awe, the mystery that propels us to keep exploring. Imagine, for a moment, that you are floating in space. The stars shine brightly around you, their soft glow painting the dark canvas of the cosmos. You drift weightlessly, suspended in a sea of silence, when a thought arises. What is it that keeps the planets in their orbits, that makes things move the way they do in this vast, empty space? The answer, as you will soon discover, is not something you can touch or see, yet it is everywhere. It is the very nature of space itself. Space, in its simplest form, is not just an empty void in which things happen. Instead, space is a dynamic, ever-changing fabric that stretches and bends with the presence of matter and energy. This concept, the curvature of space, is one of the most profound and beautiful discoveries of modern physics. It tells us that space is not flat, not a smooth, empty plane, but a flexible, malleable fabric that can curve and twist, creating the very structure of the universe. The idea of curved space comes from the work of Albert Einstein, who, in his theory of general relativity, showed that gravity is not just a force between two objects, as we once thought. Gravity, he proposed, is the result of mass and energy bending the fabric of space-time. Imagine laying a sheet of fabric flat and placing a heavy ball in the center. The fabric dips, creating a curve around the ball. Now, imagine rolling a marble across the fabric. The marble will spiral towards the ball, not because the ball is pulling the marble in the traditional sense, but because the fabric itself is curved in such a way that the marble follows the curve. This is how mass and energy bend space-time, creating what we experience as gravity. This curvature is not just a theoretical idea. It has real consequences in the universe. The Earth, for example, is constantly moving through space, and the curvature of space-time is what keeps it in orbit around the Sun. The Sun, with its immense mass, creates a deep curve in space-time, and the Earth follows that curve, perpetually falling towards the Sun, but because of its motion, it keeps missing the Sun, creating the elliptical orbit we experience. It is the same with the Moon and the Earth. The Earth's mass causes space-time to bend, and the Moon, caught in this curve, orbits the Earth in a delicate dance. If you could somehow see the curvature of space around the Earth and the Sun, you would see it not as a simple flat grid, but as a deep, swirling curve, with the planets and moons following the paths created by that curvature. These paths are not straight lines, but curves, and it is in these curves that the dance of the universe takes place. The curvature of space-time also explains why light bends as it passes near a massive object. When light travels through space, it follows the curvature of space-time, and if it passes near a massive object, like a star or a galaxy, the path of the light is altered. This phenomenon, called gravitational lensing, allows us to see distant objects in the universe in ways we never could before. We can observe light from stars and galaxies that are far beyond our reach, their light bending around massive objects, creating an arc of light that reaches us. This bending of light is direct evidence of the curvature of space-time, showing us that even the path of light is not immune to the influence of gravity. Now, imagine the entire universe, from the tiniest particles to the largest galaxies, moving through this curved space-time. Everything, every star, every planet, every particle of matter is affected by the curvature. The force of gravity is not a mysterious force acting at a distance, but a result of the way mass and energy shape the very fabric of reality. It's as though the universe is woven together, each thread pulled by the curvature of space-time, creating the beautiful, intricate tapestry that makes up the cosmos. But the curvature of space is not just limited to the motion of planets and light. It also affects time. Space and time are not separate entities, but part of a single four-dimensional continuum known as space-time. The curvature of space-time affects not only the motion of objects, but also the flow of time. This concept is known as time dilation, and it can be observed in extreme conditions, such as near a black hole or at very high speeds. Time moves more slowly near massive objects because the curvature of space-time is so deep. Imagine that you are near a black hole, a region of space where the curvature is so intense that nothing, not even light, can escape. As you approach the event horizon, the point of no return, time slows down. To an outside observer, it would seem as though time itself has frozen, as though the very fabric of reality is stretching and distorting. This bending of time and space is not just theoretical. It has been confirmed by experiments. For example, scientists have measured the difference in the passage of time between two clocks, one on the surface of the Earth and one in orbit. The clock in orbit ticks slightly faster than the clock on Earth because the curvature of space-time is slightly different at different altitudes. These small differences in time, though almost imperceptible to us, are proof of the profound way that space-time bends and shapes the universe. So, what does all this mean for you as you drift through this vast, curved reality? It means that the universe is not just a collection of objects moving through a void. It is a living, breathing thing, shaped and molded by the very fabric of space-time. The curvature of space is what gives rise to the beauty and the order of the cosmos. From the orbits of planets to the paths of light, it is this bending, this curving of space and time that holds the universe together. But even as you float in the stillness of space, you realize that there is still much we do not understand. How far does this curvature extend? Is it limited to the regions of space we can observe, or does it stretch beyond the edges of the known universe? What happens when space-time itself is bent beyond the limits of what we can measure? These questions continue to inspire wonder and curiosity as scientists and explorers seek to understand the mysteries of space-time. In this moment of quiet reflection, you are reminded that the universe is not just a place to be explored, but a reality to be understood. The curvature of space invites you to look at the cosmos in a new way, not as a flat, empty void, but as a dynamic, interconnected fabric shaped by the forces of nature. It is this curvature, this bend in reality, that makes the universe not just a place of stars and planets, but a place where time, space, and matter dance together in perfect harmony. Imagine the universe as a vast, intricate tapestry stretching across the limitless expanse of existence. Every star, every planet, every atom is woven into this fabric, held together by forces that are often invisible but deeply felt. This tapestry is known as space-time, a concept so profound that it reshapes how we view everything from the flow of time to the movement of the stars. Space and time, which were once seen as separate, are revealed to be part of a single, unified fabric that governs the very structure of reality. The idea of space-time comes from the work of Albert Einstein, whose theory of relativity forever changed our understanding of the universe. Before Einstein, we thought of space as a vast emptiness where objects moved through time in a linear fashion. We believed that time ticked the same for everyone, everywhere, and that space was like a stage where events occurred. But Einstein's insight revealed something more. Space and time are not fixed. They are flexible, malleable, and inextricably linked to one another. Together, they form the fabric of the cosmos, a unified entity that bends, stretches, and warps, with the presence of mass and energy. To understand this, imagine a large sheet of fabric stretched out before you. If you place a heavy ball in the center, the fabric bends, creating a dip. Now, if you roll a marble across the fabric, it will spiral inward toward the ball. This is a simple way of visualizing how mass and energy bend spacetime. The heavier the object, the greater the curve it creates in the fabric. This bending is what we perceive as gravity, not an invisible force pulling objects towards one another, but a result of the curvature of spacetime itself. The presence of mass distorts spacetime in a way that objects move along the curves created by that mass. The Earth orbits the Sun, not because it is being pulled by an invisible force, but because the Sun's immense mass causes spacetime to curve in such a way that the Earth follows the curved path, caught in its orbit. Similarly, the Moon orbits the Earth, tracing the curves of spacetime created by the Earth's mass. But the curvature of spacetime is not limited to planets and stars. It affects everything from light to time itself. When light passes through space, it follows the curves of spacetime, just as a marble rolls along a curved surface. Light bends as it travels through the gravitational wells created by massive objects. This phenomenon is known as gravitational lensing. When light from a distant star passes near a galaxy or a black hole, the spacetime curvature caused by these objects bends the light, allowing us to see distant galaxies that would otherwise be hidden. The very path of light is shaped by the fabric of spacetime, bending and twisting around the objects it encounters. But spacetime does more than just guide the movement of objects and light. It also governs the flow of time itself. Time, as we experience it, is not the same for everyone. The curvature of spacetime causes time to pass at different rates depending on the strength of the gravitational field you are in. This is known as time dilation. For example, the closer you are to a massive object, the slower time moves for you. If you were standing near a black hole, where the curvature of spacetime is extreme, time would slow down dramatically compared to someone far away from the black hole. To an outside observer, it would seem as though time had stopped for you, but to you, everything would appear normal. The universe would continue on, but in a different rhythm, shaped by the deep curvature of space-time. This idea of time dilation has been confirmed through experiments, such as those involving atomic clocks placed on airplanes. Scientists have found that the clocks on the airplanes, moving at high speeds, ticked slightly slower than those on the ground, confirming that the passage of time can be affected by motion and gravity. The fabric of spacetime does not just stretch out around objects, it also stretches out around time itself. Perhaps the most profound aspect of spacetime is its dynamic, living nature. Spacetime is not a static background upon which events unfold. It is an active participant in the cosmic drama. As mass and energy move through the universe, they cause ripples in the fabric of space-time, just as a stone causes ripples in a pond. These ripples, called gravitational waves, are produced when massive objects like black holes or neutron stars collide. The waves travel through space-time at the speed of light, carrying information about the collision with them. These waves were first predicted by Einstein, and in 2015, scientists were able to detect them for the first time, confirming that space-time itself can vibrate and ripple in response to the motions of massive objects. These gravitational waves provide a window into the most extreme events in the universe, events that would otherwise be invisible to us. They allow us to hear the universe in a way we never could before, as the fabric of space-time itself carries the echoes of cosmic collisions and cataclysms. The discovery of these waves opens up a new way of exploring the universe, a way that lets us sense the very vibrations of space-time. As you think about the fabric of space-time, you begin to see that it is not just a theoretical concept, but something that shapes our everyday lives. The GPS satellites orbiting the Earth must account for the effects of space-time curvature in order to give us accurate location data. Time moves differently for the satellites than it does for us on Earth, and without adjusting for this difference, the GPS system would quickly become inaccurate. In a sense, we are always moving through space-time, carried along by its curves, shaping our experience of reality. But even as we begin to understand space-time, we realize that there is still so much we don't know. What is the true nature of the fabric of space-time? How does it behave in extreme conditions, like the center of a black hole? What happens when space-time is warped to the point of creating a singularity, a point where the curvature becomes infinite? These questions remain at the frontier of scientific exploration, as physicists continue to seek a deeper understanding of the very fabric of the cosmos. In this moment of reflection, you understand that space-time is not just a backdrop for the universe, but the very structure that makes it possible. It is the stage on which the cosmic drama unfolds, the medium through which we experience the universe. It is a living, breathing fabric shaped by mass and energy, and through it, everything is connected. From the smallest particles to the largest galaxies, everything is woven together by the threads of space-time. You float in the vastness of space, where the stars shine like distant diamonds, their light slowly reaching across the unfathomable distances of the cosmos. In this quiet, timeless expanse, you may notice something unusual, something that, until not so long ago, was a profound mystery. The universe, it seems, is not just stretching out in all directions. It is accelerating as it expands, speeding up as if some invisible force is pushing it forward, driving galaxies apart at an ever-increasing pace. This force is known as dark energy, and though it is one of the greatest mysteries of modern science, it holds the key to understanding the ultimate fate of the universe. Dark energy was first suspected when scientists noticed something extraordinary. In the late 1990s, by observing distant supernovae, powerful explosions of dying stars, they discovered that these supernovae were dimmer than expected. The dimming of light suggested that they were farther away than anticipated. In other words, galaxies were moving away from us faster than they should have been, based on what we knew about gravity and the expansion of the universe. This unexpected acceleration led to the hypothesis that some force was at work, counteracting the pull of gravity and pushing galaxies farther apart, and so dark energy was born, a force that is invisible, undetectable, and yet has a profound effect on the universe. But what exactly is dark energy? Unlike matter and radiation, which interact with light and can be seen or detected, dark energy does not appear to interact with anything in a way we can directly observe. It is not a substance. It doesn't emit light, nor does it reflect it. Instead, it is a kind of energy that fills the space between galaxies, exerting a force that causes space itself to stretch. This mysterious force is thought to account for about 68% of the total energy content of the universe. The remaining energy is made up of dark matter and regular matter, the stars and planets, the galaxies, and everything else we can see or detect. So, what role does dark energy play in the universe? To understand its influence, we must first consider the nature of the universe itself. The universe has been expanding ever since the Big Bang. But that expansion was initially slowing down due to the force of gravity pulling galaxies back toward one another. Gravity, as we know, is an attractive force, and it should have been working to slow down the expansion of space. However, something changed. Over time, the expansion of the universe began to accelerate, as if gravity itself was being overwhelmed by some unknown force. This is where dark energy enters the picture. Scientists theorize that dark energy acts as a repulsive force, pushing galaxies apart and driving the expansion of space at an ever-accelerating rate. This acceleration is one of the most profound discoveries in cosmology, and it suggests that the universe is not only expanding, but doing so at a rate that is increasing over time. At first glance, this idea may seem counterintuitive. After all, if gravity is pulling everything together, how can something push it apart? The answer lies in the nature of dark energy. Dark energy is not like the forces we experience every day. It does not pull or push in the way gravity does. Instead, it is thought to be a property of space itself, a kind of anti-gravity that causes space to expand. It is not a force in the traditional sense, but a fundamental energy that exists throughout the fabric of the universe. But why? You might wonder, do we not see dark energy in the same way we see other forces? The answer is that dark energy is extremely diffuse, spread out evenly throughout space. Unlike matter, which clumps together to form stars, planets, and galaxies, dark energy does not accumulate in any one place. It is everywhere, but its effects are only noticeable when we look at the universe on the largest scales. In the empty voids between galaxies, dark energy reigns supreme, driving the cosmic expansion that we observe. The true nature of dark energy remains one of the greatest mysteries. In modern physics, we do not yet know what it is, how it works, or why it behaves the way it does. One possibility is that dark energy is a property of space itself, as Einstein once speculated with his concept of the cosmological constant. This idea suggests that empty space has a kind of energy that over time causes the expansion of the universe to accelerate. Another possibility is that dark energy is something even more exotic, perhaps related to quantum fields or unknown aspects of physics that we have yet to discover. The study of dark energy has led to many breakthroughs in our understanding of the universe, but it has also raised more questions. If dark energy continues to drive the expansion of the universe, what does this mean for the future of the cosmos? If the expansion accelerates indefinitely, the universe may eventually reach a point where galaxies are so far apart that they can no longer be seen from one another. This scenario, known as the Big Freeze, suggests that the universe will continue to grow colder and emptier over time. As stars burn out and galaxies drift away, leaving behind a dark, desolate expanse. Alternatively, if dark energy behaves differently than we expect, it could lead to other possible fates for the universe. Some theories suggest that the expansion could eventually slow down, reverse, and collapse in on itself in a big crunch, where all the matter in the universe is pulled back together. Others propose that dark energy could cause the fabric of space to stretch so violently that it tears apart, a scenario known as the Big Rip. But for now, these possibilities remain speculative, and dark energy continues to be a key focus of cosmological research. As you drift through space, contemplating this mysterious force, you begin to see how dark energy plays a central role in the story of the universe. It is the silent driver of the universe's expansion, the unseen force that will shape its future. While we cannot see dark energy directly, its influence is felt everywhere, shaping the large-scale structure of the universe and determining its ultimate fate. In the quiet of this cosmic journey, you realize that dark energy is not just a mystery waiting to be solved. It is a reminder of how much there is still to learn, how much of the universe remains hidden from our view. Dark energy is like the vast, unseen ocean beneath the surface of reality, shaping the world we see and guiding the universe toward its distant future. Imagine standing on a quiet hill under the night sky. The stars twinkle faintly above, distant and ancient, each one a beacon from a past long gone. Yet there is one star that beckons to you more than the rest, not one that shines brightly, but one that offers a silent invitation to look deeper. This star is not a star at all, but a signal, a guide into the vast unknown. It is the Hubble Space Telescope, and it has offered humanity the most profound window into the universe's past, the Hubble Deep Field. The Hubble Deep Field, HDF, is not a single star, nor even a planet or galaxy, but a tiny patch of sky, no bigger than a grain of sand held at arm's length. Yet, in this seemingly insignificant portion of the cosmos, the Hubble Space Telescope captured one of the most extraordinary images in the history of science. It was an effort to peer deeper into the universe than ever before, to look further, back in time, to see what the universe looked like billions of years ago. This image, taken in 1995, was the result of an extraordinary amount of time and patience. For 10 consecutive days, the telescope focused on this tiny patch of sky, exposing the camera to the faintest light from the farthest reaches of the cosmos. The result was a breathtaking image, one that changed our understanding of the universe forever. What appeared as a seemingly empty region of space revealed thousands of galaxies, many of them so distant that their light had taken billions of years to reach us. The Hubble Deep Field became a cosmic time machine, showing us not just the universe as it is today, but the universe as it was in the distant past. Each galaxy in the image is not just a collection of stars, but a snapshot of the cosmos from a time long before our own. The galaxies in the HDF range from the relatively nearby, just a few billion light-years away, to those that are so distant. Their light is a glimpse into the universe's early history. Some of these galaxies are so far away that the light we see from them has been traveling for nearly 13 billion years, almost as long as the universe itself has existed. The Hubble Deep Field was groundbreaking for several reasons. First, it showed that the universe is far more complex and rich than we had ever imagined. The thousands of galaxies captured in the image were not scattered randomly across the universe, but each was part of a vast cosmic web connected by invisible forces drifting and stretching in the vast expanse of space. These galaxies, though distant, are the building blocks of the universe, the places where stars and planets are born and die. The image revealed a universe teeming with galaxies, each a universe of its own, filled with stars, planets, and the mysteries of creation. Second, the HDF provided a glimpse into the past, offering a view of the universe as it was billions of years ago. The farther away a galaxy is, the older the light we see from it. The light from the most distant galaxies in the HDF has been traveling for nearly 13 billion years, meaning that we are seeing them as they were when the universe was still in its infancy. This gives us a unique perspective on the early stages of galaxy formation, star birth, and the evolution of the cosmos itself. The galaxies in the HDF are not the mature, well-formed objects we see today, but fledgling structures, still in the process of coming together, still gathering the gas and dust that will one day form new stars and planets. By studying these ancient galaxies, astronomers can begin to piece together the history of the universe. They can learn how galaxies form, grow, and evolve over billions of years. They can trace the journey of matter from the Big Bang through the first moments of galaxy formation to the present day. The HDF is like a time capsule, preserving the early history of the universe, waiting to be unlocked and understood. But the Hubble Deep Field is not just a snapshot of the past, it is also a window into the future. The more we learn about the distant past, the better we can understand the future. By studying the formation of galaxies, astronomers can predict how galaxies will continue to evolve, how they will collide and merge, and how stars will continue to form and die. We can begin to map out the future of our own galaxy, the Milky Way, and consider how it will evolve over the next several billion years. The Hubble Deep Field is a powerful reminder of the vastness of space and time. When we look up at the stars, we are not just looking at light from distant suns. We are looking at light that has traveled across time and space, a history of the universe encoded in every photon. In this way, the universe becomes a kind of living history book, each star and galaxy a page that tells the story of its past. The HDF is also a humbling reminder of our place in the cosmos. When we consider how small and fragile our planet is in comparison to the vast expanse of the universe, we are reminded of the incredible scale of the cosmos. Yet, even in this immense and seemingly infinite space, we are connected not just by the stars, but by the light that travels across time to reach us, bringing with it the history of the universe. But the Hubble Deep Field is not just an image, it is an invitation. It invites us to continue exploring, to look further, to ask bigger questions. What lies beyond the galaxies in the eight left? What secrets remain hidden in the dark corners of the universe? As technology advances and new telescopes are built, we will continue to peer deeper into the universe's past, each new image offering a clearer, more detailed view of the cosmos. Perhaps one day, future generations will look back at the Hubble Deep Field and marvel at how much we have learned since then. They may even have their own deep fields to explore, looking farther back in time, uncovering new chapters in the story of the universe. But for now, the Hubble Deep Field serves as a reminder of how much we have already discovered and how much more there is to learn. Imagine you are floating through the vast, silent expanse of space, far beyond the reaches of stars and galaxies. In this quiet void, there is a whisper, a soft hum that fills every corner of the universe. It is a faint, almost imperceptible glow, not from the stars, but from something much older. This light is the cosmic microwave background, CMB radiation, the faint echo of the Big Bang itself. And it is the oldest light we can observe in the universe. The CMB is often described as the afterglow of creation, a remnant of the universe's birth. It is the light that was released when the universe, in its earliest moments, transitioned from a hot, dense soup of particles to the vast expanse of space we see today. This light has been traveling through space for nearly 13.8 billion years, and it is a direct link to the universe's infancy, offering us a snapshot of the cosmos when it was just a few 100,000 years old. To understand the CMB, we must first look back at the beginning, at the moment when the Big Bang occurred. The universe, in the earliest moments after the Big Bang, was unimaginably hot and dense. The energy was so intense that atoms could not form, and instead, the universe was filled with a turbulent soup of particles, protons, neutrons, electrons, and photons. These photons, or light particles, were constantly interacting with matter, scattering in all directions, unable to travel freely through space. But as the universe expanded and cooled, something remarkable happened. Around 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine and form hydrogen atoms. This process, known as recombination, allowed photons to travel freely for the first time, as they were no longer constantly scattered by the dense, hot plasma. These photons, now unimpeded by matter, were released into space, and they traveled outward, carrying with them the imprint of the universe's early conditions. This released radiation is what we now observe as the cosmic microwave background. It is a faint glow, uniform across the sky, but not the bright light of stars. Instead, it is a cooler, softer radiation with a temperature of just 2.7 Kelvin, nearly absolute zero. This radiation permeates all of space, filling the universe with a gentle hum, and it is a key piece of evidence for the Big Bang theory of the universe's origin. The CMB is a treasure trove of information. It holds clues about the very early moments of the universe, the conditions that existed when the cosmos was just beginning to take shape. By studying the tiny variations in temperature and density in the CMB, scientists can learn about the distribution of matter in the early universe, the formation of galaxies, and even the age of the universe itself. To understand this more deeply, imagine that the early universe was like a boiling pot of soup with pockets of higher and lower temperature. The CMB is a map of the universe. From that time, showing us where the denser regions were, the areas where gravity began to pull matter together to form galaxies, and where the less dense regions were. These tiny fluctuations in temperature are the seeds from which the large-scale structure of the universe grew, creating galaxies, clusters of galaxies, and vast cosmic voids. The CMB is also a reminder of how far we have come in understanding the universe. When the CMB was first discovered in 1965 by scientists Arno Penzias and Robert Wilson, it was a moment of profound revelation. They had unknowingly stumbled upon a signal that was predicted by the Big Bang theory, confirming that the universe had a beginning and that it was evolving from a hot, dense state. The discovery of the CMB helped solidify the Big Bang as the leading theory for the origin of the universe, and it opened a new era of cosmology, where the past, present, and future of the cosmos could be studied with the light of the CMB as a guide. Today, scientists continue to study the CMB using advanced instruments like the Planck satellite, which has mapped the CMB with incredible precision. These measurements have provided us with some of the most accurate information about the universe's early history, including its age, composition, and the rate at which it is expanding. The CMB has helped us answer some of the most profound questions about the universe, but it has also raised new questions. How did the universe evolve after the Big Bang? What is the true nature of dark energy, which is causing the universe's expansion to accelerate? And what happened in the moments immediately following the Big Bang when the universe was still in its infancy? One of the most fascinating aspects of the CMB is how it connects the past to the present. When we look at the CMB, we are not just looking at ancient light. We are looking at the very foundation of the universe. The light we see today from the CMB is the same light that has been traveling through space for billions of years. And it is the same light that filled the universe when it was young. The CMB is a cosmic time machine, allowing us to peer back into the earliest moments of the universe and trace the evolution of space and time. In this sense, the CMB is not just a relic of the past. It is a living, breathing reminder of the universe's ongoing journey. The universe continues to expand, its light stretching across time and space, carrying with it the story of creation. As we study the CMB, we are not just uncovering the history of the cosmos. We are also learning about our place within it, about how the universe has shaped us and how we continue to shape it. As you float through this cosmic journey, looking at the faint glow of the CMB, you realize that the universe is not just a distant and unknowable thing. It is a part of you, just as you are a part of it. The light that fills the universe, the radiation from the Big Bang, connects us all across time and space. It is a reminder that we are all woven into the fabric of the cosmos, and that the universe, in all its vastness and mystery, is not something distant and unreachable, but something that is with us, always, always. Beneath the vast canvas of the universe, a faint whisper persists. It is the cosmic microwave background, or CMB, the afterglow of creation itself, emerging about 380,000 years after the Big Bang. It carries the imprint of a time when the universe was a mere child. As the cosmos cooled, light began to travel freely, filling the universe with a faint warmth we still detect today. This ancient radiation, though invisible to our eyes, touches everything around us. It's in the background hum, the song of the universe itself, echoing through the cold vastness of space. Scientists, like cosmic detectives, interpret the CM as a map of our universe's infancy. It reveals the temperature fluctuations that later gave rise to galaxies, stars, and everything we know. It's as if the universe has left us a photograph, showing us not just its current form, but the story of its birth. And as we study the CMB, we are not just exploring the past, we are glimpsing the future, seeking answers to what lies beyond. Imagine standing on the shore of an endless ocean, gazing at the horizon. The farther you look, the more the ocean stretches, but what lies beyond that horizon? This is the essence of our observable universe. The universe we see is limited by the distance that light has traveled since the Big Bang. This boundary defines what we can observe. What's beyond it remains hidden, a realm beyond our reach. The observable universe is about 93 billion light-years across, but we know there is more, stretching far beyond the reach of our instruments. As light travels outward, it reveals more of the universe, but it also fades, leaving parts of reality. In shadow, we can only glimpse a fraction of existence. Beyond the observable, space continues its infinite stretch, but we may never fully comprehend its full extent. The multiverse theory stretches our imagination to its breaking point. What if the universe we inhabit is only one among many, each existing in parallel to the others? In one universe, gravity might work differently. In another, time could flow in reverse. The possibilities are endless. This theory springs from the very nature of quantum mechanics, which suggests that at a subatomic level, multiple outcomes could occur simultaneously. What if each possibility gives birth to a new universe existing alongside our own? The idea that there could be an infinite number of universes, each as real as the one we call home, challenges our most fundamental understanding of reality. Yet, if there are infinite universes, might there be one where life forms that are radically different from our own exist? Could there be a universe where we are simply a fleeting thought in a cosmic mind? Black holes, those mysterious regions of space where gravity is so intense that not even light can escape, are more than just cosmic vacuums. They are doors to realms beyond comprehension. When a star collapses in on itself, it creates a singularity, point where space-time curves infinitely, and the laws of physics break down. Within this dark abyss, all known rules of the universe fail, and we are left with questions that have no easy answers. What happens inside a black hole? Does time come to a halt? Does space stretch and twist beyond recognition? Scientists theorize that black holes could serve as portals to other regions of space, or even other universes. They might be windows into the unknown, places where the very fabric of reality is distorted. The shape of the universe. What is it? Is it flat, as some theories suggest? Or is it curved, like a sphere? Or could it be shaped like a donut, twisting and looping in a way we can't yet perceive? To answer this, scientists look to the very structure of space-time itself. The universe could be a vast, flat expanse, stretching endlessly in all directions, or it could be curved back on itself, creating a closed loop. Observations of distant Galaxies, the CMB, and the way light bends as it travels through space have led to various theories. However, we don't yet know for sure. The universe may have a shape beyond our comprehension, one that we cannot see or measure with current technology. The answer might lie in dimensions beyond the three we know. Asterisk, asterisk, the edge of the universe. Does it exist? Conventional thought suggests that space is infinite, stretching on forever, with no end. Yet, when we look at the observable universe, we see a boundary, an edge marked by the furthest distance light has traveled since the Big Bang. But is this edge real, or is it simply a limitation of our perception? Could the universe curve back on itself, creating a loop where space doesn't end but instead folds in on itself? Or does the universe continue indefinitely, with no boundary to be found? Some theories suggest that the very concept of an edge may be meaningless in a universe governed by relativity, where space is fluid and ever-changing. Asterisk, from the first steps on the moon to the distant probes sent beyond the solar system, humanity has always sought to explore. But space is vast, and our reach is limited. We have touched only the smallest fraction of the universe. Yet, even with the fastest spacecraft, it would take thousands of years to reach the nearest star. The challenges of human space travel are immense radiation, resources, and the physical toll on the body. Despite our technological advances, we remain bound by the limits of our biology and our tools. Our dreams of distant galaxies and star systems may one day come true, but for now, we must acknowledge the vastness that remains beyond our reach. Asterisk, space, could it have an end? It's a question that has puzzled philosophers and scientists for centuries. If space is infinite, it has no boundaries, no edges. It stretches endlessly in every direction, with no point of closure. But could there be a hidden limit? A point where space itself reaches a boundary, a point beyond which there is nothing. Some theories suggest that the universe is like a balloon, expanding ever outward. As it grows, new regions of space are created and the concept of an end seems irrelevant. Yet, for some, the idea of an infinite universe feels unsettling. If space goes on forever, does anything truly have meaning? Asterisk, the cosmological horizon is a curious boundary. It marks the farthest point from which light has had time to reach us since the beginning of the universe. Beyond it, we cannot see yet. Does this mean there is nothing beyond it? Or is it simply a limitation of our senses? Just as the horizon marks the furthest point we can see on Earth, the cosmological horizon marks the limit of our observable universe. It's a reminder of how little we truly understand about the vast expanse that surrounds us. Beyond the horizon, there could be galaxies, stars, and even entire universes that we will never see. Asterisk, the universe is both infinite and finite, a paradox that defies easy explanation. On one hand, it stretches endlessly in all directions, with number apparent edge or limit. Yet, on the other hand, it has a beginning, the Big Bang, a singular moment when time and space themselves were born. So, if the universe is finite in age, how can it be infinite in size? Perhaps the answer lies in the curvature of space-time itself, where the rules of geometry break down, and the infinite can exist within the finite. Asterisk, since the Big Bang, the universe has been expanding, its galaxies moving further apart. The expansion is not slowing down, but accelerating, propelled by a mysterious force known as dark energy. The fate of the universe is now tied to this expansion. Will it continue to stretch forever, growing colder and emptier as the stars burn out? Or will it eventually collapse in on itself, a cosmic implosion in a big crunch? The accelerating expansion suggests that the universe will continue to grow, leaving behind a dark and desolate future. But in the deepest reaches of space, new stars may be born, and new galaxies may emerge, continuing the cycle of creation and destruction. Asterisk, beyond the universe, what could exist? Some theories suggest that there might be a layer of reality beyond our universe, a place where the laws of physics are entirely different. Could the universe be part of a greater multiverse where multiple realms of existence intertwine? Others believe that the universe could be a simulation, a digital construct, in a far greater reality. Still, other theories propose that beyond the universe there is only nothing, a vast, uninhabitable void. Each idea presents its own mysteries and challenges to our understanding of the cosmos. Asterisk, imagine a space where more than 3 dimensions exist, a reality where time and space are interwoven into something far more complex than we can perceive. In higher dimensions, space could fold in on itself, creating shortcuts across vast distances. String theory suggests that the universe may have as many as 11 dimensions, each hidden from our senses. These extra dimensions could explain many of the phenomena we observe, from gravity to the nature of dark matter. Yet, the challenge lies in perceiving them. Our senses are attuned to a 3-dimensional world, but perhaps the answers we seek lie in dimensions beyond our reach. Asterisk, time and space, do they have an end? If the universe is expanding, is time stretching out indefinitely? Or will time one day come to a halt, its flow frozen forever? Theories about the end of time range from a slow freeze, where all activity ceases, to a dramatic collapse of space-time itself. But if space and time end, what does that mean for our understanding of existence? If time ends, does that mean history itself vanishes, leaving no trace of what came before? From the hot, dense state of the Big Bang, the universe has expanded, cooled, and formed galaxies, stars, and planets. But evolution does not end there. The universe will continue to change, perhaps in ways we can't yet imagine. Stars will burn out, galaxies will collide, and new forms of life may emerge in unexpected corners of the cosmos. The evolution of the universe is a story still being written, and though we can't predict every twist and turn, we can be certain that the journey will continue. Asterisk, space is vast, and its mysteries are endless. From the cosmic microwave background to the edge of the universe, we have only begun to scratch the surface of what exists. Some say that space will go on forever, stretching beyond our comprehension. Others believe that it may have a limit, a boundary we may one day reach. But perhaps space has no end, only infinite beginnings, a journey that stretches far beyond our current understanding. The universe is not just a collection of stars and galaxies. It is a living, breathing entity, constantly changing and evolving.